we aren't able to get to will be sent to an expert who will reach out to you directly. Please note that this webinar will be recorded and will be sent to the email address you registered with in the next few days. I'd like to hand this over to Kevin to get us started.
Hello, everybody. This is Kevin Bakke with 3D Systems. I am the Transportation and Motorsports Segment Leader for 3D Systems. That comes from having about 12 years experience in the automotive industry at an automotive OEM, as well as 12 years experience developing industry solutions and enterprise solutions around transportation, motorsports, automotive. I'm really excited to be here. This particular topic is what I would call near and dear to my heart. I spent a lot of time as an electrical electronic systems engineer in automotive, and have really dealt with, struggled with these types of applications in the EDS space. With me today is Richard Broad. He's with our 3D Systems UK office. He's an application development manager in 3D Systems in our AIG group. We're really excited to have him on this. His background, he comes with incredible experiences initially as a chemist and in materials. Importantly, he's got over 20 years experience in additive, and he's got a lot of years experience with 3D Systems and these types of applications with automotive customers. So I'm really excited to have him walk us through this application as well. I'll be handing that over in the coming minutes, but first we kind of want to walk through the agenda and just give some overview items to set the context for the application. Next slide, please. So the agenda today, I want to talk, basically I'll lend some perspective on the challenges around this particular application in flexible component retention. Then we'll walk through the design and concept phase. Richard will kind of go through, the key elements of the applications, similar applications as well. We'll talk about some of the other elements of the application or extended elements of this particular application. Some topics around retention systems and some of the important features of the application. Then finally we'll kind of summarize where we're at, and then we'll close out with question and answer. We can go to the next slide. So some of you may know already, some of you may not, but 3D Systems has recently gone through a transformation where we've really developed teams that are specifically focused on industry segments, what we call industry segments. The intent is basically to leverage the extensive knowledge, history, and so on that 3D Systems has from a technology space, but really, industrialize that. Take a look at some of the hardest problems that customers in certain industries have, and really apply the technology, and that includes the hardware, the materials, the software, the IP and knowledge from folks like Richard into the context of an industry. In this case, as I said, we're in the industrial side of 3D Systems under transportation and motorsports. Transportation and motorsports consists of not only the consumer automotive side, which we're really focusing on here, but also things like aftermarket service, commercial and public transportation, the motorsports, obviously, as well as marine and recreation. So next slide, please. Now, in order to industrialize this for transportation, motorsports, and in particular consumer automotive, what we've done is we've taken a look at that portfolio of technologies, including, as I said, the equipment, the materials, the software, the applications expertise, and really highlighted key application areas around the vehicle development process. And this is a slide kind of doing the walkthrough or walk around on a vehicle, highlighting how we've built out or subdivided these application areas. These include, common areas that I'm used to working in, like body interior and trim, body exterior panel, powertrain, under hood, also indirect applications for things like manufacturing aids and metal durable tooling. So this gives an overall landscape of the application areas that we're currently considering in consumer auto. But now what I want to do is kind of dive into where the applications are that take into account our application today, the flexible retention components. So next slide, please. So one of the things that you'll find as we go through this is the problem that we're solving here around managing flexible components, packaging those effectively in vehicle, is that it crosses boundaries between actually many applications. The two areas that we're really focusing in on is the body interior and trim space, as well as underhood and powertrain. So these are two application areas in the vehicle where we feel like this specific application could and should be applied. Next slide, please. So if we talk about the challenges that we're facing here, so I'm going to start out with increased routing complexity. So we all know, if you've been in this space, that the complexity is definitely not decreasing. It's increasing at a pretty dramatic rate. And by complexity, the things that impact this type of complexity are the types and variability of takeouts for certain flexible components, primarily EDS or wiring harness takeouts. But this also, as we'll talk about a little later, can be applied to things like vacuum hoses, fluid management systems, hoses go through the vehicle, various other wires, and so on. Basically, anything that needs to be retained and is flexible in the vehicle. The other thing that we get into is harsh conditions. So harsh conditions really are where this is going to be particularly applicable. And obviously this is going to be in areas like underhood and powertrain, where you've got high heat cycling, where you've got chemical exposure, where you've got other components that are in motion that could damage these types of flexible components. Constrained packaging space. I've never really been in a situation where we haven't had constrained packaging in automotive. It seems to be something that engineers are continually fighting over, is making sure that they've got clearances and so on that again protect those types of components. And then finally, lower volumes and customization. This particular application, I feel from a business perspective, one of the things we've struggled with is engineers could design things to package and protect these types of components, but when it came to the economics of producing them at lower volumes, when you have higher variability, lower marketing take rates, the business model kind of fell apart. So the intention here is to deliver this technology so that you can build at lower volumes, kind of more custom solutions to solve these packaging constraint problems. So that's the challenges that we're looking at. Next slide, please. So now we'll go into the design concept phase, and I'm going to hand this over to Richard so he can really walk through some of the details and illustrate the application. So Richard, it's all yours.
Thank you, Kevin, and hello everybody. As Kevin's already discussed and put the application into context, the benefits of additive manufacturing here are manifold, and they're ideally suited to the demanding requirements of retainers for flexible components within the automotive environment. Because the freedom of design and lack of manufacturing constraints, we can think completely out of the box in terms of part complexity. Specifically, things like tool design and the constraints of tool design are completely disregarded in this context with additive manufacturing. It's actually how we end up with the phrase digital tooling. It means that the features of the parts being designed and manufactured via additive manufacturing can be considered throughout the whole life cycle of the product. Not necessarily just in its intended use. So from manufacture and processing to installation and end use and even servicing and replacement. It also means that not only can the part be designed for conformal geometry for fitment and fixing, but also for the ability to assemble with guides, retention features and closures. Importantly, these features don't need assembly prior to installation, but can be included in one single part. And when I say features, I mean features such as clips, covers, closures, channels for zip ties, and the like. The simple case we're demonstrating here gives us the ability to highlight some of the abilities of additive manufacturing in retention parts. This example is a retention device for an automotive door wiring harness. The part is relatively simple in its design, but it's fairly feature-rich in terms of application and function. The solution choice is often depicted by material properties, and in this case, the choice of material, figure 4, rigid 140C black, is the ideal solution. Rigid 140C black is a new high-temperature material, as the name suggests. It's a rigid, heat-resistant material combining high strength and high elongation for toolless direct plastics production. Next slide, please. In particular, there's some key points to highlight that evolve the approach to design and manufacturing workflows used for a part like this. Assemblies of connectors and retainers can be combined and refined into single components. For example, fluid junctions in cooling lines, and things like multiple angles within the same component are things that can be considered, i.e. not constrained by traditional tooling constraints. Complex components with no limitation on enabling features can be achieved. So again, moving away from those constraints of injection molding. The part can be totally optimized for its intended use, with precise conformal fit within any space on a vehicle, and with any kind of accessibility. That's kind of pertaining back to the serviceability point that I made earlier. The space that the part occupies and the space around it can form part of the design to ensure that the areas otherwise thought of as inaccessible or too complex to fit a part into can be used. By incorporating the fitting guides into a part, assembly also becomes much easier and without error. And for full product traceability or control, things like QR codes are something that we've developed and been experimenting with, and can be incorporated as part of the additive manufacturing into individual components. The design of the code that we've developed has specifically been developed to have a real readable contrast, as you see on the picture on the slide there, with some element of translucency through the QR code to enable reading of the code itself. Next slide, please. So as an example of the design freedom, the harness retainer part we're demonstrating here as some features that can be included and adapted as the design and design environment changes and evolves. I'm just going to try and share my camera, and then I can point out some of the features on this part. This part is a really great example, as it's feature rich, fairly simple part, but fairly feature rich. And I'll just try and see if I can highlight some of those features as we go here. The geometry of the retainer itself is a great example of the design freedom and ability to conform to tight spaces and provide better packaging reliability and functionality. This part had to fit within a particular corner on some of the pressed metal surfaces within the door assembly, and distribute elements of the harness accurately within the space. So if you see the geometry of the part here, you'll see some routing for the harness itself down each of the individual channels. This then distributes the elements of the harness into the right spaces. The geometry of the part itself, you'll see, is essentially a 90-degree right angle fitting into the corner of a door skin or a door assembly. Within this part, there are standard fitment accommodation, so a hole here and some other bosses and holes here within the part, and those can accommodate things such as push pins or rivets or spring clips, or fir tree fasteners can be housed, for example, and that gives you the ability also to create standoffs and fitting guides. This case also gives you an example of a method to secure the harness via channels that house zip ties. So if I can show you this carefully on the camera, you see at each of the ends of the guides here, there are some channels which are designed for zip ties. But that's just one simple solution that can be manipulated to suit the environment and application that takes into consideration the assembly workflow and servicing requirement, for example, for ease of use and accessibility. Focusing on the assembly of parts, of course, the geometry nesting features that can be used with additive manufacturing help with installation of the retainer itself. But on this part, there are some guide hooks. Hopefully you can see those on the part here. I'll try and keep the part moving so that it's fairly clear. But the guide hooks on this part are designed to allow the harness to be installed quickly and easily and accurately, whilst providing support to the harness until it's actually fastened into position with the zip ties. There's also a small example, a relatively small example of lightweighting on this part around the bosses for mounting the part, which obviously has obvious effects. And as an example of, again, the benefits of additive manufacturing, the assembly aids can be individual parts in themselves. The part that you see in the lower left picture on the slide there is a drilling guide that carries many features designed to perfect a step in the process of a fitment of a component in a transportation application. Things such as separate vacuum channels for placement, holding and debris removal, drilling guides with sequencing, standoffs for maintenance of vacuum placement are just a few things that can be incorporated. Next slide, please. Okay, our previous example showed the application with the use of zip ties as the method of fastening to the harness to the retainer. As another example of the functionality of 3D Systems additive manufacturing solutions, there's a multitude of possibilities. And this is an example of another retaining device that exploits the ability to design a hinge and clip feature, reducing further the need for assembly. Material choice is key here in the enabling the hinge and clip features to function as a single use or even multiple use items. And with the growing range of materials for Figure 4 specifically, and across the board of 3D system solutions, really, the choice is becoming more and more simple. Next slide, please. So I focused on the benefits of additive manufacturing for the retainer design and function, but there is an element to this that obviously within the manufacture and the production of these parts that is a key element of consideration. So there's several elements to consider here. First, we've developed the Figure 4 to achieve real production quality parts with excellent surface detail and finish. There's little user input required for downstream processing in the same way there would be for injection molded parts. This really is the foundation of the idea for toolless manufacturing, or if you like, your USB stick or your network connection to transfer build data to the machine becomes your tool. Second is the ability to stack parts within a build that gives real efficiency in operator input time. In this case, the stack's been designed for cleaning and performance. The third point is that the investment costs of such a system compare really favorably against traditional manufacturing methods, particularly for low volume production with the ability to iterate designs without costly tool changing. Fourth is the locality and lack of complication in the supply chain. Parts can be made on site and just in time for assembly. There's no need for things like stock on shelves or associated delays of shipping stock from point of manufacture to point of use. And I think fifth is really based around costs throughout the workflow for the life cycle of the part. And that's where we're talking about the ability to optimize the design, produce locally just in time, streamline the assembly and so on. As a rough indication, the total production time in this case for the stack that you see on the slide there is about 1 hour 48 minutes per part to a complete finished part. Now That sounds like a lot compared to traditional production techniques, but there's some really key considerations to take into account, as I explained, alongside the fact that this requires no tool design or manufacture, which of course often can take weeks, if not months, at considerable cost as well. Next slide, please. Just as an example, there are routes to streamlining the production of parts with Figure 4 and additive manufacturing in general. And those can be, multifaceted. There's this is the same part. This is a taller stack and a different material. In this case, I think this is Pro Black 10. And as you see here, the times are significantly reduced. The total build time per part on this stack with this material becomes roughly around 34 minutes. And it's important to point out here again that as per the last case, the minimal manual post-processing time of less than 2 minutes per part. That's without any automation. Once we consider all things like automation, in a true additive manufacturing production scenario, then that time can be cut significantly, or the total time for CAD to part can be cut very significantly. Next slide, please. So as anyone can imagine, there are really many existing applications for automotive retainers. And as Kevin mentioned, the complexity of vehicles is growing day by day. And the requirement for component complexity is following that trend, and the capabilities for those components are following the same trend. As we move towards new powertrains, hybrids, electric vehicles, then we're seeing that the requirement for things, for retainers of harnesses, hoses, and other flexible components is continuing to grow. And we think that additive manufacturing solutions, and particularly with the advent of some of the new materials that 3D Systems is developing for Figure 4 and other volume production additive manufacturing, is really suited very well to these kind of applications. Next slide, please. So how has 3D Systems addressed and met the challenges of flexible component retention applications? Realistically, I think it's by the creation of a solution by developing the individual components as a package. When we talk about a package, when we talk about a solution, we're talking everything from the original CAD design, so software, through to component manufacture with hardware and materials, but also quite importantly with the knowledge as well. It all starts really, and as Kevin mentioned, my involvement through the last 20 years with additive and particularly resin systems, the developments in the last few years in materials technology and the kind of materials we're focusing on here has really opened up the ability for additive manufacturing in a production kind of a scenario, particularly with automotive and transportation applications. Next slide, please. So as I mentioned, production applications really require proven production grade materials. The advent of what we're talking about here, Figure 4 platform, and materials available for that platform opens up all sorts of opportunities that can be taken advantage of, and take advantage of the design freedoms that I've already mentioned. Our efforts in material development and solution development have taken a really novel approach in R&D, and as in my experience is the culmination of an approach that is application led and designed from the ground up to achieve the right end result. So in order to ensure we can compete against traditional thermoplastics, which is really the basis of what we're talking about here, we've really strived to ensure that our material data sheets carry the most comprehensive data that is that's relevant to the envisaged application areas. Importantly for automotive, that's carrying out the reported and proven accelerated aging testing, both indoor and outdoor, showing retention of mechanical integrity with exposure to common fluids and chemicals, and showing mechanical isotropy. Our data sheets for some older materials, generally stereolithography, used to only really run into 2 pages of data at the most. If you were to look at our newer data sheets, you would see that our figure 4 materials are extensively tested. There's a wealth of data on there to show that these materials really do stack up well in those kind of environments. To some extent, our older data sheets showed the limitations of some of the traditional materials, and I guess what I'm saying here is that there's a real night and day difference between some of the older versus the newer materials we're talking about here. But the data sheets are designed to give you all of the information that a design engineer and you as additive manufacturing users, all of the information you need to make an informed choice with the confidence of the material's abilities. Next slide, please. So enabling parts to perform in a production environment means having a range of materials that are suited to everyday applications. Often requirements of an engineering part is that it's resistant to many external forces, such as temperature extremes, as is often very common. Well, we know is very common within the automotive space. Temperature extremes and fluctuation, impact resistance, and UV and moisture resistance. In automotive applications, for example, temperatures range from -40 to +120 degrees C. And these materials will accommodate that quite easily with little loss in mechanical performance. For specific automotive applications, it's genuinely, in my mind, it's genuinely exciting to see the abilities of these 2 materials in particular. And I think these are a real step forward in what can be achieved. Figure 4 rigid 140C black that we've discussed already here produces true functional durability in plastic parts. The material includes a patented filler that provides toughness, and it can be comparable to injection molded polybutylene glass fiber. Under the hood, components produced with this material have performed really well and reliably under HTOL, or high temperature operating life testing, and it's currently tested to the equivalent of 8 years indoor and 1.5 years in outdoor environments per ASTM automotive testing standards. And those figures are quoted, and there's data quoted on our data sheets. HDT is obviously an important factor, and as the name suggests, HDT of 140C is at the lower pressure. Importantly, we've also have a material that fits with the evolution of automotive powertrain. Figure 4 high temp 150C FR black is a rigid, importantly flame retardant black material that can achieve ULV-V0 rating, as well as the equivalent FAR ratings. It's another material that's ideally suited for transportation and aerospace applications